Hi everyone. What is hashing? What or which algorithm or concept do you think of when you hear the term hashing? I'd like you to type that in the chat. So to give an overview of what I will be presenting, so first I'll discuss algorithm or concept, not algorithm or concept, but generally accepted description of hashing. Then I'll give an example implementation in Python, and I also present an example of hashing that I used recently in a project. Thereafter, we will look at the properties that establish a secure or cryptographic hash function. We will review a timeline of hash functions and discuss what the future holds. There will be time after the talk for questions. As Alex said, we can also talk in the chat. So with that, let's jump in. So the quote says, secure hash 256 is very strong. It is not like the incremental step from MD5 to secure hash 1. It can last several decades unless there's a massive breakthrough attack. So the quote is interesting to me for several reasons. First, it was written by Satoshi Nakamoto, who is the supposed alias of the person or persons who created the Bitcoin. They authored a white paper and deployed Bitcoin's original reference and the first blockchain database. So that is a lot of street cred. It also indicates that the hash function can be substantially stronger than its predecessors. And it shows that there's something like an arms race for hash functions where they need to be continuously updated to survive the onslaught of clever and brute force attacks. So let's look at the description of hashing. So hashing is the process of using an algorithm to map data of any size to a fixed length hash value. So it can be text, it can be a table, it can be a music concert, it could be a full-length movie. In the middle, we have the algorithm or hash function, which produces a message digest, which is usually rendered as a hexadecimal number. But of course, in machine code, this is just zeros and ones. So I look at the responses, see Git and passwords and blurus, which I've never heard of. I see there's a winking face. And these are all good responses. But a simple example that we often use, but may not come to mind first, although it's in the name, is just a hash table or hash set. So the hash table is a direct access, high performance data structure where a large amount of data is to be stored and accessed quickly. We can input a string, so in this example, Karen, and we then get an integer hash value. We can then get a hash value modulus of the array size, and from that, get an index position. So ideally, each string is inserted into a unique index position, and there are no overlaps. In this case, we can use the table for fast writes and reads. So an implementation of the hash table is the dictionary in Python. So let's look at an example where we are tasked to find how many times the letter A appears in this quotation by Samuel Beckett. So it's try again, fail better. So if you look at the T's, it appears 1, the R's appear twice, the Y appears 1 time, the A's appear 6 times, and one more, the G's appears twice. So we can go through the whole quotation and get the unique count or the count for each unique letter and store that in our dictionary. So the Python hash function returns integer objects. They are always represented with 24 bytes on a standard 64-bit Python interpreter. and they must be immutable types. So we see if we take the hash of 1, we get 1 back, hash of 10, we get 10 back, a decimal number, we get a different integer, a hash of a string, also some integer, and if you take the hash of a non-immutable type, it gives you an hashable type. If you look in the bottom code block, we see that a collision has occurred and the same index was matched, which implies that the same hash value was generated. As we said, the index position is the hash modulus the array size. So this is a fine hash algorithm, but it made use of a concept called separate chaining, which consists of a chain of values in the same bucket or index position, and it uses another data structure, usually a linked list, to create, to add the values. The problem with that is that you have to scan the entire linked list if you need to look for a specific value. Of course, that is worst case, will be a linear big owned value. Another way of addressing this issue is the open addressing strategy, where if the bucket you should use is busy, you just keep searching for a new bucket to be used. And you have to initialize your bucket with a default value and keep looking for an empty bucket if the one you should use has already been taken. So dictionaries in Python are built using hash tables and the open addressing collision method. So now for a different example. So I was tasked last year to prevent duplicates in a large number of CSV files that were imported into Elasticsearch. These were huge audit logs that's continuously uploaded. The client had a problem that their files were sometimes uploaded more than once and duplicates were created. So how could we prevent the duplicates? So firstly, I want to say that Elasticsearch is a NoSQL database, and it's based on a Lucene indexing engine, which is optimized for searching and analytics. So the records had the format as shown here: a date, invoice number, a product, quantity, and a price. And we see that the first 2 records are duplicates. The client had another requirement that if we get a record which only differs in 1 or 2 fields, we should only update the fields and not overwrite it. So some of you might be thinking, why don't you just use sort unique? And like I mentioned, the problem was that we get several files and you cannot just continuously concatenate all the files together and sort them to get all the unique values. So it had to be solved in the database. Luckily, Logstash conveniently provides a fingerprint function, and this is in its Elasticsearch filter, and it creates a hash function, or it creates a hash or a fingerprint from these fields. So here we use the date, invoice number, and product field, and we use the secure hash 1 method to create a unique fingerprint. So the fingerprint was used as follows. If the fingerprint exists in Elasticsearch, we update only the fields that changed. If it doesn't exist, we create a new record. So enough of Elasticsearch. Let's talk about hash complexity. We see here the binary digits for a secure hash 1 output. So each bit may be in one of 2 states, a 0 or a 1. So that is 2 times 2 times 2 times 2 up to 2 to the 160 possible permutations or arrangements of the bit digits, which is quite a lot. It is smaller than the number of atoms in the observable universe, which is 10 to the 78. for a comparison, secure hash 256 gets a bit closer if you wiggle a 0 at the end. So these are large numbers, but there are mathematical properties that makes finding a match between the hashes much more likely. The one is the pigeonhole principle, which simply says that if you have 9 pigeonholes and 10 pigeons, 2 must obviously share a hole. So you can see the 2 in the left top share 1 pigeonhole. So this leads to the birthday paradox. So which says that there is a 100% chance that 2 people, usually at the birthday party, will have the same birthday out of a group of 367 people. I think they take leap years into consideration. So what is surprising of this birthday paradox is that only 23 people are required to have a 50% chance of a match, according to probability theory. Of course, this assumes an equal probability of birthdays, but this paradox works well for something called the birthday attack, where we have a random attack attempts on a fixed number of hash permutations. So it is possible to find the collision in a hash function within the square root of 2 to the n attacks. For secure hash 1, it works out to 2 to the power of 80. This brings us to the properties of a secure hash function. So say we have an initial value, in this case a human, and a hash function. So think of the Hitchhiker's Guide to the Galaxy and the spaceships being converted into toasters and fridges. And a hash output, which is limited to a fixed-sized alien. So the first property is that the hash function, the secure hash function, must be one way. It's also called pre-image resistance. This means that it should not be possible, should be very difficult to get an initial value from the hash. So it is relatively easy to create a hash, but almost impossible to find the initial value from the hash. So the second property is that hash functions must be second pre-image resistant. This is also called target collision resistant or weak collision resistant. And this means that we know an initial value and the hash it produces. We should not be able to, and they often use the term, it should be infeasible to find another initial value that produce the exact same hash. So you can think of the input value as being your name and the hash function as being your unique way of creating a signature or signing your name. If someone can forge your signature, they can buy a cruise ship, write you into their will, or sign up for Scientology. If they have your name and an example of your signature, it will be much easier to forge your signature. A third property of a secure hash function is that it should be collision resistant. This is also called strong collision resistance. So it should be extremely difficult to find 2 initial values that produce the same hash. So here we are not exposed to that pre-image, but choose 2 input values randomly. So we need to calculate the hash for potentially all hash permutations to find 2 that match. The fourth property is that it should produce a pseudo-random output. So this does not mean that the hexadecimal number will look weird or something, but just that it's so unexpected that it might as well have been random. The fifth property is non-malleability, or without a clear pattern. This often ties in with the avalanche effect, where a small change in the initial value results in a major change in the hash value. So even though our initial value changes only slightly, we see the shirt color only changes, the output is very different for no apparent reason. So now for a history lesson. now my history edition is not loading. All right. So let's just see if I can do it here. Well, this timeline nightlab is quite a nice tool to use to create timelines, and it's usually online. Except in this case.
Eval just posted in chat that everything that Google's down. Yeah, Google is down. That's one step before apocalypse, I think.
Okay, so what I want to show with the timeline was that we had to, sorry, there's going to be no images for these. So I'm going to say, give the ones that I remember. So in the 60s, we had our first hash functions that were created based from researchers that work on encryption. And I wonder if it's worth just reloading it. Sorry. Let me just reload this.
Yeah, it's working in the southern suburbs. Come on, Deep South. Come on. Louis, do you know about not paying your AWS bill?
Okay, something's happening. And we're back to this slide. And we have live, it's alive. Okay, so the evolution of hash functions can be seen in how their construction changes over time. So different hash functions were developed that made finding collisions harder and harder. Oops, sorry. So initially in the 60s, hash functions were based on block ciphers. These were used by researchers in encryption. So it made a lot of sense for them to reuse those designs and the evaluations of the block ciphers. It was also a more compact implementation. The disadvantages were that it was limited by the block length, which was 64 or 128-bit long, and it couldn't increase. And of course, those can be broken very easily today. It also was based on weak keys DES and the key schedules AES. In 1989, Professor Ronald Rivest created the MD2 algorithm, which had the 128-bit hash, and that was optimized for the best technology at the time, which was 8-bit computers. In 1990, he created the MD4, which was 128-bit hash, and today that can be broken in seconds. In 1992, the MD5 was created, Haval, the ripe MD, and the MD5 was 10 times faster than this. What was more significant is that it required no license, and it was much easier to export than an encryption algorithm. What I mean with that is that it was much easier to apply it in software. So in 1993, what was later to be called the Secure as 0 algorithm was created, and it had a 160-bit hash, which is it's a significant step from 128 bits. That was created by the NSA. In 1995, we had Secure Hash 1, which was an upgrade. Then a few years later, in 2002, the Secure Hash 2 group of algorithms were created, also by the NSA, and they used a slightly different construction internally. In 2007, the Secure Hash 3 competition was announced. And yeah, since 1998, there were various papers published that showed that the previous secure hashes could be broken in fewer steps than brute force, which we learned was 2 to the 80 steps. We also, secure hash 2 could be broken in more than 24 steps out of the 80 that it uses. So the nest hash function competition was an open competition. In 2008, the researchers announced that they created a rogue CA certificate using MD5. It made it possible to impersonate any website on the internet. What is whispered is that they required all these serial numbers from certificate authorities that they had to buy up to make the attack possible, but MD5 can be broken in seconds today. Then in 2008, the Ketchak algorithm was created, and it used a sponge function construction, and it was based on the radio cartoon construction. It was very different than the MD5 and previous secure hash algorithms. Then in 2011, NIST officially deprecated the secure hash 1, and it's interesting, the well-known security expert Bruce Snyder noted that a collision attack is therefore well within the range of what an organized crime syndicate can practically budget by 2018 and the university research project by 2021. In 2012, we had the Blake 2 algorithm based on Blake, and Blake 2b, interestingly enough, is 3 times faster than Ketchak and is used in some implementations of Ethereum. In 2012, the SHA-3 competition winners were published, and Ketchak was first, became secure as 3. Runner-up was Blake, and MD6 was also up there. So in 2015, NIST announced that secure hash 3 had become a hashing standard and should be used. Then in 2017, the secure hash 1 collision was found by researchers at Google and Amsterdam. And here is an infographic that talks about the collision. Basically, they did some bit manipulations on 2 PDF files to make them appear exactly the same. So just to go back, you will see the only difference between them is the color. So the one that just have a blue background, the other one a red background. But they produce the same secure hash 1 hash output. This is a bit small, so but for secure hash 256, it's a very different hash, as one would expect. So, as they mentioned, the potentially impacted systems, document signatures, SSL, version control, and backup systems. They use 9 quintillion steps to break it, and compared to, let me just explain this a bit, compared to other collision attacks, MD5 can now be broken in 30 seconds with a smartphone. Their algorithm, 110 GPU, was able to find the collision in 1 year. And with brute force, 12,000 GPUs Pentagon will take a year. So that's quite a bit more. What can you do to defend? You can move to SHA-256 or SHA-3 as a replacement. You can test your PDFs on the shatter.io website. It's well worth looking at that website. Google already protected with that. And yeah, as I said, the team was Amsterdam and Google researchers. So then in 2020, Blake 3 was created. And notably, it's much faster than the predecessors, MD5 Secure Hash and Blake 2. And also notably, it's more secure, unlike MD5 and Secure Hash 1, that's obviously been broken. So my bets are on the Blake 3 is probably all used already for Ethereum and in the blockchain environment. Then what does the future hold? So NIST does not currently plan to withdraw the Secure Hash 2 or remove it from the revised Secure Hash standards. For quantum computers, the theoretical collision for brute force is in 2 to the power of n/3, which is a bit faster. And interesting, one can use something called multi-hash to allow one to easier upgrade your current algorithms to the latest. That might be something that Linus Torvalds want to use in his GitHub. So what I hope is clear from the timeline is that creating a new secure function often takes several years, but a hash can be broken at any time. Different hashes serve different purposes depending on the design and hash speeds. A faster hash algorithm is necessary when the user experience is important. For example, when creating a secure connection to a website. When the hashing algorithm is used to store a password, we care more about the complexity, and slower speeds are acceptable when it increases the security. So for a quick recap. So hashing is an extremely useful technique for creating a fixed size message addressed from a variable size initial value. Hashing may be used to speed up algorithms or to add a layer of security to sensitive data. Secure hash functions must be one-way, second pre-image resistant, collision resistant, pseudo-random functions, and have no clear hash relationship with the initial value. Secure hash functions must continuously evolve to keep up with technology, the latest application, and attacks. It often takes a few years. Also, secure hashing may be seen as a digital fortress with firewalls and network zoning being the wall. But once this has been breached, we are only left with encryption. This is terrifying if your digital fortress controls a nuclear facility or the chemical concentration at your water plant. So given that secure hashing protects these as well as your banking account, and with social media, perhaps your reputation, could it ever be secure enough? That concludes my talk, and I thank you very much.